guys, how are you? So in today's session we are going to talk about the K-means clustering. K-means clustering is an machine learning algorithm where we use this algorithm to make some clusters. Like let's say you have a given raw data of a population and you have to make five clusters of that population, or let's say you have to make n number of clusters. So this K-means clustering is very useful technique for implementing those. And if you are not aware that how many clusters you have to make, so this came by we I just also tell you about some tricks like how you use this k-means clustering for making the for deciding that how many number of clusters you have to make. This k-means clustering also provide that. So let's start with this. And K-means algorithm is an iterative algorithm that tries to partition the dataset into k predefined distinct non-overlapping subgroups clusters where each data point belongs to only one group. So here the k-means algorithm is like iterative. It is an iterative algorithm. It is an making an loop n number of times and tries to partition the data into k predefined distinct overlapping subgroups where like every data point is considered as a single group. So that's what clustering is. First of all, the first step of this k means clustering, it tries to make the intra cluster data points as similar as possible while also keep the cluster as different far as possible. So it tries to figure out figuring out the whose cluster are similar to each other and whose cluster are not similar to each other. It assigns data points to a cluster such that the sum of squared distances between the data points and the cluster centroid arithmetic mean of all data points that belong to that cluster is the minimum. So it just like in the k means, like if you want to make five clusters, so there were five centroids and every centroid is tried to minimize the distance, the mean distance of all the data points which came under the that class of the centroid. The less variation we have within cluster, the more homogeneous similar the data points are within the same cluster. So as we have the less mean arithmetic mean of the data points that belong to the clusters, the less variation we have, the more homogeneous, the more similarity we get in that group, the more similarity we get in that cluster, and we get a more clear picture of some n number of clusters. Next, the way k-means algorithm works is as follows. Specify number of the cluster scale. So first of all, we have to specify the number of clusters, how many clusters we want to make in our k-means clustering, like, and we assign a variable like k, like k is equal to 5 means we have to make five number of clusters. Initialize centroids by first shuffling the data set and then randomly selecting data points for the centroids without replacement. So basically it first shuffle the data set and then randomly select the k points, some n number of k points, set of k points like 1 2 3 4 5, and without replacement it keeps iterating until there is no change to the centroids, that is assignment of data points to the cluster isn't changing. So basically what is do, like you have thousand number of data points and you just pull out your thousand number of data points on the graph, then you selectively choose k number of points randomly. Like if you want to make five clusters, then you select randomly five points as a centroids, and you try to figuring out the number of distances between the that 5 points or that centroids to the other points, and try to minimize the distance between those points and the centroids. Like in the first phase, you take a point as a centroid, and you see that the point which is nearer to that, if we consider that point as a centroid, then the total sum of the distances is become less. So that's how you keep shifting the points and get the and change the shifting the centroid. And when the centroid position isn't shifting, then you Consider as now we get our clusters. Compute the sum of square distances between data points and all center points and all centroids. Assign each data point to the closest cluster centroid. Compute the centroids for the clusters by taking the average of all data points that belong to each cluster. So few things to note here. Since clustering algorithms including k-means use data distance based measurements to determine the similarity between data points, it recommended to standardize the data to have a mean of 0 and the standard deviation of 1, since almost always the features in any dataset would have different unit of measurement such as age versus income. Next is like given k means iterative nature and the random initialization of centroids at the start of algorithm. Different initializations may lead to the different clusters, since k means algorithm may stuck in a local optimum and may not coverage the global optimum. Therefore, it's recommended to run algorithm using different initials of centroids and pick up the result of the run that yielded the lower sum of squared distances. So yeah, basically what is saying that when you try to randomly choose some centroids, sometimes it gives an error, sometimes it doesn't choose the correct cluster. So you have to run this k-means clustering algorithm some two or more than two times, like 5 times, 3 times, to see that if the clusters are making in the correct format or not by visualizing them. So elbow method gives us an idea on what a good number of clusters would be based on the sum of squared distances SSE between data points and their assigned clusters centroids. We pick K at the spot where SSE starts to flatten out and forming an elbow. We will use the geyser dataset and evaluate SSE for different values of K and see where the curve might form an elbow and flatten out. Sometimes we use the term WCV within cluster variation for saying about the sum of squared distances. So here I will explain it by using a graph like this. I just plot this SSE or the WCV on this graph, and this is the number of clusters. Like the square of distance between the clusters is this much. If I have the one cluster, if I have the two clusters, then the square number of distance is very less. So in the squared sum of distance is less, and in 3 we get more less, and in 4 we get more less, and so on we get on the less sum of squared distance value. So as you can see from graph, we can say that two clusters can be made from that data. Like here you can see we get an elbow from at the point of 2. So we can say that in our in our dataset we can say that we can make two clusters, and 2 is the optimum number of clusters to make. So that's how we use this elbow technique to find out the optimum number, good number of clusters. And ideal clustering is like we take three centroids. As you can see, first of all we take centroids at, let's say we take these three centroids, 1, 2 and 3, and we calculate the distance for this centroid for the points which are nearer to this. Then we calculate the distance between this centroid to other points which are nearer to this, and we calculate the distance between this centroid and the other points which are nearer to this point. And when we get the distance from all those points, let's say this centroid have take the distances for all of these points. Now this now we calculate, now we get again the centroid for according to these data points, like the which centroid is good for all of these data points. And when we shift our centroid, we shift this centroid from this, and we shift this centroid from this, and this centroid is kept it as here. Now we again calculate the distance between this centroid and this centroid to other data points, and we shift our centroid again, so that in order to get the less minimum distance between the data points, minimum distance between all the data points to the to their respective centroids. So as we keep on shifting our centroids, we get our ideal clustering, we get our clusters, total number of clusters as we want. So this is the ideal clustering case. In real life, we don't get the clusters which look like this much clear, this much ideal. Now, applications of this k-means clustering algorithm. Algorithm is very popular and used in variety of applications such as market segmentation, document clustering, image segmentation, and image compression, etc. The goal usually when we undergo a cluster analysis either get a meaningful intuition of the structure of the data we are dealing with, cluster then predict where different models will be built for different subgroups if we believe there is a wide variation in the behaviors of different subgroups. An example of that is clustering patients into different subgroups, build a model for each subgroup to predict the probability of the risk having heart attack. So these are the simple applications of this k-means clustering algorithm, which has a huge on them. And here are some drawbacks. K-means algorithm is good in capturing structure of the data. If clusters have a spherical like shape, it's always trying to construct a nice spherical shape around the center. Like it is, as you can see in this, it is trying to make a spherical shape. And let's think that it is a blank plot, and I will show you. Like let's say we have a this much plot, and some data points are in this format, and some data points are in this format. So from this graph you can say that we have two clusters, one is this and one is this. But but if we use this k-means clustering, then it will assign these part as one group and this part as a one group, which we don't want. So that's the drawback. So that's a drawback of this k-means clustering algorithm. And now let's move on to other point. What are the other drawbacks? That means the minute the clusters have a complicated geometric shapes, k-means does a poor job in the clustering. Like if we have other shapes, complicated geometric shapes, like let me draw something. Like we have a graph here, and I have a draw shape like something like this, and we have a data something like in this shape format, and we have another data in something like this shape format, and another data which is surrounding all of these two. So if we apply k-means clustering, then it will make something clusters like this and this, which is wrong. We want a clustering technique which will specify this outer points and this single line and the inner circle in a differentiate manner. So in this format, this k-means clustering is not performs very well, and this is the drawback of it. We will illustrate three cases where the k-means is not where we will illustrate three cases where k-means will not perform well. First, k-means algorithm does not let data points that are far away from each other share the same clusters, even though they obviously belong to the same cluster. Below is an example of the data points on two different horizontal lines that illustrate how k-means tries to group half of the data points of each horizontal lines together. So basically, I draw this example for you. Just wait a second. Like, yes. So let's say we have a plot and we have some data points in this format. We like we have this line and we have another this line. Like we have a data which are, if we see in a plot, then we can say that it is seems to be like a two parallel lines. And when we try to apply k-means clustering on it, then the k-means will take a centroid something like this or this, and will make a spherical shape. Like one is shape is here, and by taking another centroid here, it will make a shape here. So which is wrong. We know that these are the no two these two clusters are not correct, and what we want in actual, okay, what is happening, yeah. So what we want in actual is that we want an algorithm which say that this single line is one cluster and this another single line is another cluster. So that's what this example is telling about. That below is an example of data points on two different horizontal lines that illustrates how k-means tries to group half of the data points on of each horizontal lines together. So that's about these examples, and that's about the drawbacks. Like, what are these drawbacks of this k-means clustering? So yeah, now that's on all the drawbacks, and after this theoretical session, now we are going to move on the coding session, where I will tell you that how you can implement this k-means clustering technique.